almost 5 years before joining the university at Canberra in late 1998. Besides teaching, he has been actively pursuing research related to neural networks, fuzzy logic, evolutionary computing, intelligent systems, optimization, data analytics, modeling of complex adaptive systems, decision support systems, and data security and privacy, and their applications in industrial, financial, and business problems, which involve real-time data processing, planning, and decision-making. His current research interests lie in adaptive self-learning systems, fuzzy logic, genetic algorithms, neural networks, and application of computational intelligence techniques for learning and adaptation of intelligent systems and intelligent agents, data security and privacy, web-based application filtering, data mining, cloud computing in public sector. He has successfully completed many industry projects related to real-time data processing, planning, and decision-making. To date, he has edited 24 books and conference proceedings in computational intelligence and intelligent agents. He has written more than 150 refereed publications in the form of books, book chapter, journal articles, conference papers, and many more. He has chaired 14 international conferences on computational intelligence, intelligent agents, and software engineering. Professor Masood Mohammed has 27 years of academic experience, and he has served as a program committee member and co-chair of many national and international conferences. He has the chair of IEEE ACT section, and he was the recipient of awards from IEEE from USA and Ministry of Commerce from Austria, and several awards for his academic services in Australia. May I invite you, sir, to introduce our speaker of the day. Please welcome.
We have a lineup of a great speaker today, among many great speakers we had. Professor Panos Lassisas has a diploma in electrical engineering from the University of Thrace in Thrace and a PhD in electrical engineering and electronics from the Control Systems Center at the University of Manchester. He commenced his academic career at the University of Manchester before joining City University of London in UK, where he was a professor of image processing and head of the electrical and electronic engineering department. Panos is currently the department chair of computer science at Khalifa University of Science and Technology in Abu Dhabi. He is the author and co-author of approximately 200 research publications in international journals, book chapters, and conference proceedings. Recently, he was the program chair of 19th International Conference in System, Signals, and Image Processing. He has over 25 years of experience in development of image processing, machine learning, and intelligent systems. It is with my great pleasure to invite you to deliver your keynote, please.
Thank you. It's a pleasure to be back here at AMITY University campus in Dubai. So the title of my presentation is Mathematical Morphology Classification, a New Paradigm in Machine Learning. So I would like to share with you some recent results that we have in this type of approach. As our chair earlier mentioned, I'm working in image processing and machine learning, so some of the ideas for this type of machine learning algorithm, in fact, originated from image processing. So in my presentation, I will start with a brief overview of classification and supervised learning. I will then give you a very light touch or an overview of what mathematical morphology is in the context of image processing. And then I will introduce our paradigm, which is the morphological classification, followed by two algorithms. The first one is known as morphological KNN, and it's an extension of the traditional K-nearest neighbor classifier. The second one is the morphological dilator, which is based on the dilation operation in mathematical morphology. I will talk a little bit about implementation issues, specifically how we tackle some of the challenges relating to this type of approach, and then I will give you the experimental results that we carried out in sort of like a large category of traditional machine learning problems with comparisons with state-of-the-art classifiers. And finally, I will conclude and give some, so let's say, directions for future research. For those of you that are not familiar with classification, of course, it's a supervised learning approach. This means that for like an input pattern, you have a label, a target, and in this type of approach, we basically analyze the information of the labeled instances, so the instances that are attached or assigned to classes, and the process of supervised learning, or the outcome, is basically to generate a model which is capable of producing a mapping or learning the mapping from the input space to the output space, the space of classification, and then to utilize this space, or this model rather, to classify unknown instances, so instances that do not have a label. There are many paradigms for classification algorithms. For instance, k-nearest neighbors, which would be one of the classifiers I will work with in order to develop an extension in terms of the morphological framework. Linear discriminant analysis is another very popular type, LDA. Neural network approaches, multi-layer perceptrons, radial basis function networks, so like more theoretical and sophisticated approaches such as support vector machines, then like approaches which are more easy to interpret, such as decision trees, and then approaches that combine probabilistic and tree, frameworks such as random forests. What is the challenge for a supervised learning approach or for a classifier? Basically, the challenge is how do we infer the distribution of patterns in feature space, as in like, how do these patterns look like in feature space, based on the limited samples that we have from the training set. And typically, this is solved in terms of an optimization approach. So we are trying to minimize an error criterion, which is a cost function. And we do this by adjusting some free parameters which are obviously associated with our model. So these free parameters could be the weights in a neural network or the hidden units, or it could be, let's say, the depth of a decision tree, and so on. So I'm showing you here like an example of a machine learning problem. And what you can see is that there are two classes in this problem that we are trying to separate, the red and the blue class. And you can see that the problem is nonlinear because I cannot find a line that would optimally separate between the two classes. And it's nonlinear because, of course, we have this subset of the blue class, which is surrounded by the red class. And I'm showing you some decision boundaries as they are discovered using traditional machine learning paradigms. So you have the decision boundaries as they are being established by the KNN classifier. But the issue here is how do I choose the number of nearest neighbors, so this number k here, that I would need to optimally choose so that I can separate the samples of the class. Then you have another decision boundary here, which is found using a multi-layer perceptron. But the issue here is how do I decide the optimal number of hidden neurons, assuming that I have a single layer only to play with. Then you have another approach or another result here with decision trees, where the boundaries are not as non-linear as in the previous approaches. They are more piecewise linear. But the problem is, how do I enforce consistency with this type of classifier? Because if there is a slight change in the data, then the decision boundaries are going to look quite different. And finally, I have random forests. But there is an issue here. How do I reduce the bias of this particular classifier to multi-level features. Really, the thing that motivated our research in terms of this mathematical morphology classifier is that all of these classifiers, they're basically attempting to learn the distribution of patterns in feature space. So, but actually none of these techniques uses sufficient information about the spatial distribution of the patterns. How do they look like? They have sort of like fixed models. For instance, the model could be a probabilistic model, it could be a Gaussian distribution, it could be a mixture of Gaussians that I haven't discussed. But actually, they are not using the data themselves as a starting point. So, this is really, I'm going to skip this transparency, but basically the things that you need to sort of like pick up from this transparency is that really the problems that we deal with are nonlinear. And they're nonlinear because typically a class is not just sort of like, it's not present in a single sort of like area of space, but typically classes are scattered in multiple parts of the feature space, and therefore you have what we call subclusters. That if they're been put together, then you can generate sort of like a set that contains all the instances of a particular class. Of course, because of the way that we deal with problems, so because of the way that we choose to approach the problem of fitting a model, sometimes, because we don't know the real distribution of the data themselves, sometimes we overfit the model. Possibly because sometimes there is noise in the data and actually the complexity of our model does not fit well with the level of noise in the data. So we decided to sort of like look into a new approach which is based on morphology. So mathematical morphology is sort of like a tool in image processing in particular, whose aim is to basically manipulate the shape of the data, the shape in 2 dimensions, or if you like, the morphology or the p-dimensional shape in multiple dimensions. And we wanted to see whether we could come up with some kind of like classification model that could then be used in, of course, supervised learning methods. So just like an essence about mathematical morphology, it's about the analysis and the processing of geometric structures, and it's based on set theory. It applies to digital images, but basically it can be used on graphs, on surface meshes, and other spatial structures. And the main operators of mathematical morphology are dilation, erosion, and then you have a number of like composite operators based on these 2, which is, for instance, the opening, the closing, the top hat transform, reconstruction, and so on. So what is dilation? I'm going to talk about this a little bit in terms of binary images, so black and white images. For every mathematical morphology operation, you define a structuring element, which is sort of like a small object with on and off pixels. And you can use this model or this structuring element as a means of like manipulating your image or your set, if you like. In the context of dilation, when we apply dilation, we basically expand an object or a shape, and you have here the definition of dilation. So basically what we do is that we take each of the pixels of the structuring element, or if you like, we express those pixels in terms of coordinates, and then we shift the pixels of the object by those coordinates, and then we take the union of all of those sort of like sets. We have an extension of this to gray level, which adds the 3rd dimension, which is the intensity information. But in essence, the approach is really the same. and I have an example here, and this is really what we're going to explore in this particular technique. So we have the object here, we have this cross-like structuring element. So typically, the pixel in the middle would have a coordinate 0, 0. The pixel to the north might be -1, 0. The pixel to the south, 1, 0. The pixel to the left, 0, -1. The pixel to the right, 0, 1. So I have all of these coordinates. I apply them on each of the pixels of the object, and basically when I do dilation once, I get these new pixels, which are in light green, I guess. So I'm expanding my object. And the concept is that through this process, I'm preserving some of the morphological properties of the object, because my operator is based on that, on this sort of like concept. And what you have here is the equivalent sort of like application in gray level images, but we will not use that. Erosion is the opposite of dilation, so it typically makes an object smaller. This is our formula here. So for erosion, we do the same process as dilation, but the difference is that rather than using the original structuring element, we use its reflected version. And rather than use the union of the corresponding sort of like subsets, we use the intersection. So because we use the intersection, the result, of course, is going to be a smaller sort of like image. This is the definition for gray level. And this is now an example. So I have this structuring element. This is my object. When I apply this structuring element to that object, the result is that. So the object is shrunk. I'm not going to use erosion in my mathematical morphology classification, but I wanted to show you what are the two basic operations, like the addition and the subtraction in standard sort of like algebra. And then you have the extensions of this. So the closing is a dilation followed by an erosion. The opening is an erosion following by dilation. These again are sort of like operators that I would like to exploit in the future in terms of the concept of classification. So the essence of our approach is this paragraph here. We want to expand pattern sets of labeled instances such that the expansion or the expanded set covers the entire feature space while preserving the morphology of the original clusters, or classes if you like. So how do we do this? We, of course, identify where our classes are, which are basically in disjoint sets. And we start expanding those sets, starting from the original state at iteration I = 0, using some kind of morphological function to their final state, I = L. So in this respect, our approach is very much data-driven. Depending, although we use the same operator, the model is actually based on how the original data looks like. So this is actually a standard definition. We basically come up using this particular function with a predicted class for, so we have an unlabeled instance X. We apply a function and the label of that instance is equal to L and the assumption is that this instance X now belongs to a subset that is attached to label L. So if I was to now take the union of all of these subsets for class 1 to up to class L capital, and if I was to put them together at their final iteration, once the entire space has been expanded, then I would get C, where C would be sort of like a grid, so a discretized space that spans the entire feature space. This IL here corresponds to the number of iterations that each of the classes has to be expanded. And a class, or a subset if you like, is made up of a number of disjoint subsets which are being put together through a union operator. So this is the definition, if you like, of our operation. So it's a recursive operation. We apply the same function to expand. And this is an example again. So we have a class. I'm just showing you one class for like visualization purposes. We have a class here which is made up of a number of disjoint sets. In this case, there are 4 disjoint sets. I apply dilation once, an example being dilation with a structuring element. And what I get is this at so like iteration 1. And we do this until, for all the classes, until the entire space has been filled. So our let's say, hypothesis is that a suitable function to achieve this is dilation. We measure the accuracy of our approach, of course, by sort of like examining whether the predicted label of an unlabeled instance matches the target one, because, of course, this would be part of a testing set. And then we calculate this, the cardinality of that, and we divide it by the cardinality of the entire set of unlabeled patterns, or testing set. So we have 2 paradigms. The first paradigm is an extension of the traditional KNN. So for each, if you like, iteration of our algorithm, we visit instances which are at a distance I. So I is now the iteration number from each of the points in feature space from our unknown pattern, and we basically look for the labeled instances around them. As in the traditional KNN, we have to define what number, we have to define the number of like neighbors that we should really consider. So if this number of neighbors, or if this number of visited labeled instances is greater than this k, then we assign the majority label of those patterns to the unknown instance. Okay? So this is the mathematical sort of like definition of that. So we basically expand by taking the original data, including the union of all the patterns that are basically conforming to this function here, and this function here is given by that, which is the majority label of all the pixels which are at a distance less than I, or the most frequent label. And we have a convergence function for this as well. The second function, or the second classifier, is the dilation, which I mentioned already. Here again we use the union of the original set plus the dilations. We have a suitable convergence function here as well. Now, one problem with this kind of approach is that obviously it's very greedy, because you have to store the model, and of course the higher the dimensions of your problem, the more sort of like unreasonable or the harder it becomes to meet storage requirements. There are approaches that we are looking at for this particular problem, in the case, for instance, of high-dimensional data sets. So we're looking, for instance, at approaches that allow us to store in terms of 2 in the power of p, where p is the number of dimensions orthants, which is an extension of the quad-tree approach. So more sort of like sophisticated approaches in terms of databases. And then we're looking at implementing dilation, for instance, in this kind directly as a function, rather than implementing it in terms of a discrete grid. But for the purpose of this presentation, what we have done is that we have, and of course the contribution here, is that we are using an approach similar to random forests, where we decompose a high-dimensional problem into a combination of, or a number of 2D combinations. So we basically sort of like make the problem much more easier and faster to solve. So for a p-dimensional problem, this is the number of combinations here. P times p minus 1 over 2 that we need to consider. These problems are interlinked, and we use sort of like a majority vote to combine the outputs of those, if you like, models, or two-dimensional models. We calculated what the complexity of the this particular model is. So the complexity is the number of dimensions squared, and xt and yt are basically the discretization factor that we have in our directions. So for the simulations, we start with like some 2D problems, and then I will go to multidimensional problems. So we manipulated two popular data sets, the IRIS data set and the diabetes data set. So we reduced the number of features from 4 to 2. We kept sepal length and petal length. And the reason that we did this is because I want to show you what kind of models, to visualize the models basically in an easy way. We have the solutions here for like, in the top is the morphological KNN model, and at the bottom is the morphological dilator classifier. And these are obviously the models that we have are the gray parts. So you have a dark gray and a light gray part, and these are the actual models that have been generated by the two classifiers. And the samples that we have used to generate those models, the samples of one class are the red circles, the samples of the other class are the green squares. And I've got here like a comparison with different types of sort of like state-of-the-art classifiers. These have been sort of like the state-of-the-art classifiers are from the Weka framework. So you can see that, for instance, the mathematical KNN has an accuracy of 95%, the mathematical dilator has 95% as well, and it matches the multilayer perceptron. In terms of accuracy, though, the highest accuracy is achieved by our morphological classifiers. However, in terms of true negatives, the multilayer perceptron comes top. This is for the IRIS data set. This is the diabetes data set. Again, you can see how these sort of like models look like. In terms of accuracy, our morphological classifier has the same sort of like accuracy as the SMO classifier. In terms of the true positives, is slightly sort of like lower than the top performing one. And let me now go to p-dimensional problems. This is now where we have all features in the data sets, and we decompose the problem into 2D combinations. So what you can see for the full-blown IRIS data set, our mathematical morphology classifiers give us the top results. And what you can see here at the bottom is basically the distance from the next best classifier in the data set. In diabetes data set, the top one is the random forest, and this is the performance of our classifier, which is pretty decent. In terms of the liver disorders, the top one is the the radial basis function network, but our classifiers are sort of like close to that. The Thai data set, top one is, in fact, one version of our mathematical KNN. And the second ranked one is the random forest, followed by the morphological dilator. For another classification problem, the decision tree, and this is the performance of our classifiers. For the Haberman data set, similar performance to the naive Bayes. For the Hart-Stat log, similar performance to the decision tree. And for the breast cancer data set, we have the best performance for the morphological KNN. What I want to mention about sort of like considering all of these results together is, maybe the morphological classifiers do not give you the best performance always. but they give you competitive performance across a set of classification problems. And the parameters that you have to sort of like play with here are very limited. Only you have, of course, the K parameter for the morphological KNN, and in the case of the dilation classifier, you have the structuring element. However, the way that we choose the structuring element is to have a uniform, to look like a uniform structuring element, because we don't want to bias the directions that we're expanding our sets. And of course, we have no prior knowledge for that. This is also some sort of like comparisons in terms of training times and testing times for the 2D combinatorial application in multidimensional data sets. And you would see that actually the training times are quite reasonable. So the longest that it has taken is 13.14 seconds. Of course, once you train these classifiers, the entire feature space is pre-classified, and therefore the test times are 0 or close to 0. So in this presentation, we introduced a new paradigm of dealing with classification problems. It's actually based on a data-driven approach. It explores the structure and the form of classes. We compared it in terms of 14 well-established classifiers and 8 multidimensional problems, and the approach showed that it has the best performance in 5 out of those 8 experiments. What we want to sort of like explore further in terms of this particular approach is to develop direct, rather than decompose the problem into 2D, design direct p-dimensional approaches, explore approximations or real-time functions that generate the classification model in real time, look into data compression techniques. For instance, I mentioned earlier p-dimensional quadrants, orthants, and look into new expansion paradigms. So, for instance, fractal growth patterns would be another approach that we would like to pursue further. And this research was funded by the Abu Dhabi Education Council under an ADEC Award for Research Excellence. Thank you very much for your patience. Any questions? Yes?
Very interesting talk, thank you for that. I don't know whether you've looked at the relationship between the dilation operator and the kind of thing that pruning that can occur in decision trees, because when you prune, you get the generalization and effectively the merging of areas. I don't know whether you had thoughts on that.
Of course, so like pruning, you know, the different paradigms to sort of like optimize a decision tree would involve using mathematical morphology dilation for pruning the tree, but we haven't looked at it. It's sort of like it's a pre-existing, you know, in some respect, because it's already a set model, as in like there is already a paradigm that is based on decision tree. But thank you, that's actually a very interesting direction to pursue. We need to be able to visualize it. We need to be able to express the problem in a multi-dimensional space. So we need to decompose it into some sort of like discretized structure so that we can then apply mathematical morphology. But it's a very interesting idea. Thank you. Yes, sorry.
So you have, in your research, you have used two accuracy model for validating the results of morphology decision tree that you proposed.
Right.
There's confusion matrix, I guess.
One of the paradigms is the confusion matrix. The other ones are like standard, like accuracy, true positive, true negative.
That's confusion matrix is a part of
One of those paradigms, but you know, I haven't shown the results for the confusion matrix, which are basically broken down to individual classes.
Can we like to have more precise results
the model is not, you see, unlike other algorithms which are based on.
In your last slide, you have compared all the algorithms, J48,
Mhm.
and various others were there.
Yeah,
Like, I think hundreds of were there.
yes.
Can we use much more accuracy model to
Uh,
justify our proposed algorithm?
Yes, you mean for the proposed algorithms, you know, unlike other approaches which optimize parameters subject to minimizing an error criterion, for instance, this approach does not do that. So I cannot do anything with the accuracy results apart from, for instance, compare them, and then I can go backward, so compare them to the other classifiers, and then I can sort of like maybe attempt to change the number of k and change the number of like the way that the structuring element. But I cannot adapt any other parameters in my algorithms, and it's not dependent on the performance of the system. Right? So it does not use an optimization framework to improve the performance. This approach does not do that. Thank you. Any other questions? Thank you very much. Thank you.
Now, sir, stay here. We would like to invite our chair to felicitate the speaker with a token of appreciation in the form of memento. May I request Dean sir to step forward and join us in the felicitation. And sir, you may bring the professor along with you. I'm sorry. Presentation, yeah, to the speaker, yeah. You chair will give.
There are two pieces.
Yeah.
One is a certificate of
Sir.
appreciation, and that is a block that you can hang on your. Please stay in the middle because you're the star of today. Thank you very much for the great presentation.
Thank you so much.
You work with this?
Yeah. Okay, just a moment, sir. We would like to felicitate our chair. Is it after this? Oh.
Professor Masood Mohammad DN, who is a graduate with PhD degree from University of Central Queensland, and currently he's working with the University of Canberra. Yes. There's a long biography, but he was just to cut the thing short. His research interests are in computational intelligence, intelligent agents, and software engineering. He's also the chair of IEEE ACT section in Australia, and he has received many awards from IEEE from USA and Ministry of Commerce from Austria, and several awards for his academic services in Australia. So, Dr.
Thank you very much. Thank you for your kind introduction. And thank you for being here. What I want to talk about today is not just to present some research results, but also to emphasize something that's very close to my heart, and I've been doing research in this area as part of my research for the last 15 years. So, and the whole idea of my presentation today is to introduce you to a way of thinking, of using fuzzy logic for modeling, design, automations, and we have applied these systems in many, many problems that I will mention a few of them. And the idea is very simple in a way that software engineers, the way you break down the problems into simpler problems and solve the problems. So what I want to talk about today is also to give you a kind of vision that when you see a problem, how to approach it, but also to use fuzzy logic for problems that may not look feasible. And I will talk about this, what's the feasibility, because it becomes too complicated. And therefore you may choose other approaches like neural networks, evolutionary computing for optimizations, etc. So this is the aim of my talk today. And I thought, how do I present it? Because I will show you the robotic, multi-robot control problems, and we are trying to use the same system, and I will mention a bit briefly in a robot soccer competitions and robots that follow balls and perform certain tasks. But as you know, there's been lots of applications of computational intelligence and fuzzy logic in many, many areas, given from robotics, control of machineries, modeling, design. You have them in your camera, in the washing machines, and many, many devices. And the whole idea of fuzzy set is that their capability to handle uncertainty, imprecise results that may come from sensors, or incomplete data sets that you may have, or incomplete inputs that's coming in, or the inputs that are not 100% correct, that are coming from sensors or any device or other devices, and basically how you can handle them. The other beauty of the fuzzy logic is that it can be expressed as a set of the control rules or modeling rules or prediction rules that you can develop, and basically you can have a look at the rules, modify the rules if necessary. So it's not a black box approach. You can see what is in there. But I will explain today that when the problems become very complicated with large number of input parameters, then you will have large number of rules to solve that problem, and that makes it very difficult to inspect, 5,000 rules. And these rules overlap with each other because of the nature of fuzzy logic. So in the past, many applications of fuzzy logic was that the rules are obtained from the operators or observations or some data. And of course, you can learn the rules for fuzzy logic systems. But for those of you who are not very familiar with fuzzy logic, basically the control rules, the prediction rules, the rules that provide the solution to the problem that you want to solve is expressed in a human understandable way. When I say human understandable, that's very simple. For example, if you're controlling the air conditioning in a room, so the control rooms that controls when you turn on and off the air conditioning, or what is the speed of the fan of your air conditioning, can be expressed in a human way that we talk. Humans talk to each other. So if a temperature in the room is high, then the speed of the fan needs to be high. If the temperature is medium, then the speed should be medium, for example, or low. Of course, these high mediums are linguistic terms that we use to express. And that could be very cultural. That could be also depend on the personal understanding of the temperature. So for some people, they like high temperatures and they think it's fine in a room. So when I say the temperature is high, the high for me could be something between, I come from Australia, so I can handle temperatures up to 40 degrees. But if you come from Scandinavia, a temperature of 25 or 28 or Germany is a high temperature. Does this make sense? So these high-low terms that you see here can be adjusted. So it really, there's not a number that say, okay, when the temperature is 29, we set the fan to number 3. That's how it used to be with your fans. You know, you had a button, you press, and that's how we used to have in control systems. And as an engineer sitting here, you know, it was called bang-bang control. So temperature goes up, I go to a speed of fan 2, the temperature comes down, I go to a speed fan of 1. So, and the control system very quickly changing rather than gradual approach. And you can see in ABS systems of your cars, or you know, the self-braking cars. So you cannot suddenly apply the brake. You apply the brake slowly as you're approaching the set of lights. As the lights is changing from green to amber, you slow down. And how you put your foot on the brake, how much you press on the brake is not sudden. It's slowly, and it depends on your distance to the, your speed and distance to the set of lights. Does this make sense? So this is not something accurate that I can come with a number and say if you're coming with a speed of 60 kilometers and you're 10 meters from the set of lights and the light is turning amber, then you have to press, you know, for that much amount on your brake. Does this make sense? So, you know, similar things when you ride a bicycle. What are the control rules of riding a bicycle? Can you express how you learn to ride a bicycle? Actually, you can define the control rules, you know? You can do that. But coming back to this, this high-low, these are, of course, your input to the system is the temperature, and the output is the speed of the fan. But what we are saying, we're dividing the temperature into a set, and it could be from minus 10 degrees to plus 50 degrees, and the minus 10 to 5 degrees is cold, from 3 to 10 degrees is, to 15 is medium temperature, 15 to, or 13 to 25 is a high temperature, 25 to 50 is a very high temperature. And if you notice, I didn't say minus 10 to 5, I said minus 10 to 5 is a low temperature, a very low temperature, and then I said 0 to 10. So the sets overlaps. So suddenly you don't go from a low temperature to high temperature. The temperature increases, you know, this gradually, and gradually you feel that it's getting hot. Does this make sense? So when we talk about the sets overlap. So when I say the temperature is low, very low, low, medium, high, these are overlapping sets. Does this make sense? So when we say I'm 186 centimeters and I'm a very tall person, if you compare me with an Iranian person. But if you compare me with an Australian person, I'm not very tall, I'm a tall person. Does this make sense? It's all very subjective. Does this make sense? So a tall person suddenly is not a person that's 186 centimeters. From, for example, 181 to 188 is a tall person, and then from 186 to 2.5 is a very tall person. Does this make sense? So even if you look at it culturally or in any other way, they overlap. Suddenly you don't go from a medium height person to a tall person and a very tall person. So it's very gradual. And this is how it works. So it depends on how high is the temperature, you set how high your speed of the fan will be. Depending on how fast you're approaching a set of light, and depending on the distance that you have to set of light, you apply the brake gradually. Does this make sense? Hopefully it does. Anyhow, to build a fuzzy logic systems to model or to solve your problems, first you have to identify the inputs and outputs, like any other problem we have. What are the inputs to the system? What should be the outputs, you know, if we're controlling? So the input and output, once you know the input and outputs, you can break the input and outputs, the input and outputs into sets. So you can break the temperature into different sets, low, very low, medium, high, very high. And then you can also break your output variables, in this case, speed of the motor of the fan of your air conditioning into different sets. Low speed, medium speed, high speed, very high speed. And of course, they overlap. So once you basically know the input and output and you break them into sets, then you basically, the next thing to do is to come up with a set of rules to control the systems, right? That sounds not that bad. And of course, the input that comes to the system is not fuzzy, but we have to convert it to a fuzzy number, or to basically find out to which fuzzy sets it belongs. Fuzzy sets of high or medium or low, input and outputs. Does this make sense? So in a sense, the actual number that comes from your sensors or your data goes to the system and is allocated to depending on the value of this input and output, or input into a set. And based on the set of rules that you have, you determine what would be the output. So if the temperature is 25 and 25 is in your high range, so you have a temperature set high, which starts from 20 to goes to 35, and 25 somewhere in the middle. Does this make sense? So it's still a high temperature, but in your set of 25 to 35 degrees. And based on that, you basically apply the rule. The rule is the first rule, for example. So then you set the speed of your motor to high, and the speed of the motor to high could be a number between, I don't know, 5 and 7, whatever is how many speeds you have in your fan. Does this make sense? So the numbers comes in. It's then allocated to the, you find the sets that it belongs to. Then you basically apply the rule and find the consequence of the rule. So the temperature here is the condition. The consequence of this action of the rule is here the speed of the motor. Very simple. And then basically based on how high is the temperature, you set the speed of your motor. Does this make sense? I hope it does. But what is the problem? And that's not the, because many of you that work in the fuzzy logic know about this. So we have got the fuzzification part where the input goes in and basically applied to the fuzzy sets. For example, the temperature comes in and figure out to which set it belongs, medium, high temperature, low temperature. Then a decision-making unit, which works with the set of rules. The rules I show you is in the rule base. So you apply the rule based on the condition, which rule applies. And then the rule gives you an action. In this case was, set the motor speed to high. And then you convert your high into an actual number and return it. And how high it returns, what's the value of high as an output is depending on how high is the temperature that you're feeding in. So it actually adjusts if the temperature is high. So the motor speed high is right at the end. You're just saying it's very high. But if your temperature that falls in the high category is on the lower part, and when I say to you lower parts, imagine that high temperature is a number between 25 and 35. Does this make sense? Because suddenly the temperature doesn't become high. So for different people, the temperature is different. Anyhow, so, and based on how high is the temperature, you set the speed of the motor to a high value. And the high value could be a speed of the motor high is a number between a speed motor of 5 to 9. So if you write at the 35, so it would be 9. If you're on the lower end, it would be a speed of 5 or whatever, and in between. But what is the problem? And the rules work like this. So you have got a set of inputs. Your x's are the inputs, and y's are your output. This is the condition, and this is the actions you take on this side. Very simple, nothing complicated. The complication comes on this, because you break the inputs into sets. For example, I broke the temperature into 5 sets. Very low, low, medium, high, very high. So the line that goes from minus 10 degrees to 45 degrees, I broke it into sets that overlap with each other. The problem of having the large number of inputs and large number of sets is that your number of rules that you require for the system suddenly grows exponentially. So if you have 2 inputs, for example, in that case, we have 1 input, and we broke the input into 5 sets. So how many rules we will have? We will have 5 rules. If you have 2 inputs, and you break them into 5 sets, then the number of rules are 25. If you have 3 inputs, and you break the inputs into 5 sets, then you're talking about 125 rules. Does this make sense? And what I want to show you is, this makes it very difficult for systems with large number of inputs. Imagine you have 15, 14 inputs, and you break the inputs into 5 sets. And the reason that we break them into 5 or 7 sets is that to give more accuracy, because if your sets are you break it into 2 sets, then the overlaps and the accuracy goes down. So we break it into sets, the smaller sets, and that's the reason. So anybody knows what's the 5 to the power of 14? Over 6 billion. Over 6 billion, okay? I don't know if any of your calculator will calculate it. So, and I want to show you, before I show you the problem of multi-robot control, because multi-robot control doesn't have hundreds of inputs, I want to show you something very interesting, and I want to make hopefully stick to the time so we can make it to the lunch, is that I want to show you one problem that we solved many years ago, and we were successful, and then from that, go back to robot control. And what I want to share with you is that problem of predicting the interest rate. Predicting what would be the interest rate in 3 months' time, based on the economic indicators that economists use. That's what I want to show you. As an example, because this problem has got a large number of inputs. So we call it the course of dimensionality, and many people suggested many ways, reduce the number of rules, reduce the number of sets, get rid of some of the inputs. But as you do any of those, you reduce the accuracy of your system. Does this make sense? There are many ways, but what I suggest is solving it in a very simple way by breaking the problem into sub-problems, solving sub-problems, and then combining them together. That's what you do in software engineering. In a sense, what I suggest, or what we have done is, we have used hierarchical systems. When we basically, instead of having a system with 14 inputs and 5 sets for each input and generating over 6 billion rules, and actually you can learn the rules, and I show you, you can use evolutionary algorithms to learn the rules, but still you're talking about 6 billion rules, and when something doesn't work, how do you know which rule you have to access and what to do? It becomes very complicated. So the problem I'm showing you, and it's solved, and the details are in the paper as a reference. We broke the system of 14 inputs into a couple of fuzzy logic systems, each one generating some predictions, and then we just combine all the predictions and we got the final results. In a sense, the number of rules were reduced from 6 billion to 5,000. It's still, not acceptable. It's very high, but very good reduction. But how do we do it? Let's go into the system. We've been working this since 1996, and there are many, many papers and many masters and PhD students that went through and doing this, solving this problem. And I was one of the PhD students also, because my PhD was also in a hierarchical fuzzy control systems for multi-robot control using evolutionary algorithms. Of course, we did a comparison with the neural networks, and I show you the results of that. So what the indicators that were, this is one of the master students by research work that got the masters through doing this. And I'm presenting Mark Kingham, a student, some of his results here and some of my own results. So when we contacted the economists and said, what indicators you use to predict the interest rate? That's what economists do. And they told us, we look at the job vacancy, we look at the unemployment rate, we look at the GDP, we look at the CPI, consumer price index. we look at the household saving ratio, we look at the home loans, we look at the average earning, we look at the current account deposit, RBI index, we look at all industrial index, company profits, motor vehicles sold. Very strange, huh? Motor vehicles sold shows how well off people are in your country. If there's lots of new vehicles sold, that means people are having money to spend. Very strange, that's what they told me. I never knew that if you see too many new cars on the road, that means people are doing all right. Or, you know, if there are lots of houses being built. Or if the job vacancies are low, right? That means the unemployment is going to go up because you don't have enough jobs in the country. When the unemployment is high, you can predict that job vacancy is low. You see, they work together. Very simple stuff. After I spent a couple of years on this, I realized that. So that's what the economists use in Australia to predict the interest rate. Of course, interest rate is manipulated by government to stimulate the economy. But having, you know, for example, before election, usually the interest rate doesn't go up. You know? After the election, for a few months, nothing happens. And then things start changing. When the country starts going to recession, you can see that the interest rate suddenly comes down. And you have seen it after the financial crisis. You know, when the, for example, in Australia now, we are on a very artificial low interest rate because the government is worried that by increasing the interest rate, it will slow down the economy because the cost will go up. Cost of borrowing goes up as a business. Does this make sense? Without giving you a lecture in economy. So that's what I want you to have a look at it. And so what we did was, these are 14 indicators. And if you put all these 14 indicators into fuzzy logic system and try to predict the interest rate, you're talking about 6 billion rules that you have to come up with. So what we did was, we basically grouped the input parameters that have influences on each other directly, more directly. So have a look at here. For example, job vacancy and unemployment rate. They work together. So when unemployment rate goes up, that means there are not enough jobs in the country. When the unemployment rate goes down, like now, that means there's lots of jobs and there are not enough people to fill those, or there's not enough skill to fill those. Does this make sense? So if you look at it, these are related to each other. And we were told by economists about this, how do you group them together. All right? So the idea is here, given the current interest rate, what would be the interest rate in the next quarter? Is it going to go up, down, by how much? Right? And you have to be very accurate. And I can tell you, we came up with good solutions, but not accurate enough. You know? So we broke the system into subsystems. Now you can build fuzzy logic systems that are very simple. You know, 2 inputs, 3 inputs. The first one would have, if you have 5 fuzzy sets, for each input you will have 25 rules. The second one you would have 25, 625 or 675, 125, and I think, yeah, 125 on the last one. So in a way, now it's becoming from something that's not manageable into manageable. Because in most cases, many people will give up at this point and basically use neural networks. You just feed all the inputs into neural networks and you get the answer. You just train it, and you get the answer. What is the problem? One of the problems that I find with neural networks is you have to have large amount of data for many cases to be able, you know, to train properly. Here we're working with 20 years data. 20 years data that's collected by Bureau of Statistics in Australia. And guess how many data item is in 20 years? So every year, every quarter, the interest rate is published and decided by the government. Every quarter. So how many quarters we have in a year? Can you guess? 4 quarters. So 20 times 4 is 80 data items you have. You're talking about 80 data items that you have. That is the quarter data. 80 which are your interest rate, but also quarterly, all of these data items are collected and published. So for example, job vacancy is published 4 times a year. What was the rate? Unemployment 4 times a year. So again, you have 80 data items for each of these inputs, including your interest rate. Does this make sense? So if you're going to use neural networks, and we did actually, I show you the results with neural networks, it's not that bad, strangely. So you have to use some of them for testing, some of them for training, maybe 50-50 or 60-40, whichever you want, I don't know, you know? Let's move on, because I've talked too much, I just want to finish on time, as I said, you know. So let's move on. This is how we broke the system. That's what you saw, nothing new. Employment has got job vacancy and the unemployment rate, plus the current interest rate, or that quarter interest rate is feeding as input. The interest rate actually at that quarter is feeding to the system to predict the interest rate. So your first system predicts the interest rate based on 2 inputs, which is the job vacancy, unemployment rate, and the interest rate, to give you a prediction. The second one, the country rules, which were the GDP and CPI and the current interest rate. So to all of them, we put in the interest rate. You see the I there is the interest rate plus the other indicators going in. That's why the numbers are going to go up. So each one of them gives the prediction. Then we put in all the predictions as another fuzzy set, fuzzy systems with the 5 predictions coming from 5 groups to predict the final interest rate. Does this make sense? But why we did that? Why you put them all on the top and not feeding all of them to one? There's many ways. This could fit to that could fit to this one fit to the other one, and so on and so forth. That's another issue that I will talk about. How do you build a structure? Now you try to solve it using sub-problems. How do you link them together? Right? This is one way of linking them together. And that's the one that gives you around 5,000 rules, 5,250 rules, right? Instead of 6 billion. So this is another way to combine them together. And there are many, many other ways. Why should the employment be the first one? It could be the last one, and the foreign group could be the first one. How do you know? We don't know. It is possible to learn which one gives you the better answer. And when you learn, it's just the results comes and says, if you combine them this way, you get better results. There's no explanations using evolutionary algorithms or neural networks, actually, to guess how the structure would be. Anyhow, we use evolutionary algorithms, and I'm not going to go through this evolutionary algorithms. The plan is that we do some flipped classes. So if you're interested in evolutionary algorithms in a year or 2, you will have me talking on AMITY TV on evolutionary algorithm course and fuzzy logic and all of that. So what the whole idea is that genetic algorithm we use to learn the rules. We didn't build the rules by hand, we learned the rules for each of the groups. So basically what we did, without going to the details of genetic algorithms, what we did was, have a look at this as an example. Alpha and beta are the input, and we want to find the output. The inputs are always statics, so you know what would be the inputs, the combinations of all different sets, and you want to determine what would be the output. So creating the condition is very easy based on your input. You want to find the output, so you can basically build it very simply, very, very simply into a number and convert the number into a string of in evolutionary computing or genetic algorithm. I'm very sorry, I skip all of that, and if you get bored, you can walk away. So these are your 25 rules, for example, with the 2 inputs, rule 1 to rule 25, and then we randomly set an output set here. So for example, here's a high, medium, low, randomly generated, and then we apply the rule using the training data to figure out how good is it. We just put a fitness value, and the fitness value, how much mistakes, error was, and then we recombine. We can break this string into half, combine them together, switch them based on evolutionary and genetic algorithm rules. Very simple. And this is our fitness, absolute value between the predictions and the actual value that was generated. Very simple stuff, you know. Minimizing the error. How much time do I have? 10 minutes? Are you happy to sit 10 minutes? I can do it in 5 minutes. I can be very quick, huh? Are we running out of time? Are you hungry? No? Good? Okay, let me move on. Very easy. So once we learned all the rules, these are some parameters, you know, just for those that are interested. We had 500 population size of genetic algorithms. You know, 500 strings were generated randomly, and then recombinations and mutations. Rates are there. Number of iterations that we did to learn is 10,000. Training period was 10 years data was used for training, 10 years was used for testing. So 40 data points is not much. And here it is. Something very interesting, because when we do research, we have fun. I'll show you a couple of results. Not everything, but some of them. This is a 4 group, you know, 4 groups together. The last group was not included. Then all the 5 that you saw, all the 5 groups that you saw. So we did with 1 group, 2 groups prediction, 3 groups predictions together. So that was part of the master degree. So here is the error, training error, testing error, overall error. We also use neural networks, and this is in all the indicators feeding into the neural networks, 10 years data, and then 10 years for testing. And actually, you can check the results in training and testing. Very strange, you know, in the training, the errors was higher here, lower in neural networks, but in the testing, neural networks didn't perform as well, because you're talking about 40 numbers that were fed in. We don't have enough data in this problem. And these are just a couple of graphs that you can see the prediction and actual value. So it's very close, but not close enough, you know? So when you're predicting the interest rate, you cannot say the interest rate can be 5.7 when it's going to be 5.2. You're talking about a large amount of money that in this prediction you will lose. So a quarter of, you know, amount is very high. So it's another way of combining them together I'll show you is this. In this way, just that one feeds to this one and so on and so forth, instead of having all of them on the top and then feeding to the final. Of course, the number of rules are going to be different in this system, and we call it the feed forward. And actually, we find out that the feed forward performed better than the last one. Why? We don't know. We just combine them together, it did. And this is actually not a very good answer to give you as a professor, why we don't know. Because it depends on how you combine them. And there's many ways of you can combine them, your solution, so your sub-solutions together. So we have a better answer. And that leads to another honors and masters students going on, working on learning what's the best structure. So now we reduce the number of rules. What's the best structure to put them together? So this is just a 4 group, 5 groups, etc. This is what you saw here. If you want to know the answer, this is the predictions, training and test average. Okay. So what's the benefits? And I will be very quick. The benefit of basically hierarchical system is not only reducing the number of rules in the system, but also making it much easier to develop a solution by breaking it into sub-solutions and using fuzzy logic. When you look at the 5 billion rules, over 6 billion rules, you will just give up and you just go for neural networks or other methods, statistical methods, for predictions. But my aim here is just to show you that the problems can be broken into sub-problems and basically solving the sub-problem. So, and what I want you to take from my talk is very simple. When you see a huge problem, look at it if you can break it into sub-problems, solving sub-problems and combining them together. What we teach for a few years in software engineering. Have a look at the collision avoidance, and that's actually this is supposed to be my talk. This is the robotic systems. Imagine we have 2 docking systems, and that could be a robot that moves items to different parts. So to this docking station or that station, one moves from one direction to this, and the other one moves to another direction. And you can see the problem here. There's a couple of problems is controlling, because there's a couple of things. And depending on the heading angle of your robot, you have to take different actions. So if the robot is facing down there, you've got to turn around and go up. This is the front of the robot, right? So here again, you see that? And this one actually tried to go back. Very interesting. Never mind. But what we want to do is to control the robot. And when you think about this kind of problems, you have got two robots. You have to learn the rules to move them from anywhere in this workspace to the docking station. And imagine at the beginning their speed is constant. They go on a constant speed. And then when they get to the docking station, they have to stop, right? They cannot come with the same speed and hit the docking station. They have to slow down. So you can break it into a couple of problems. First, learn to move the robot to the docking station. One of them at a time. Imagine we have only one robot. We want to go from here to there. We just learn how to move the robot to this docking station. Just a set of rules for that. Then we learn the rules for moving the robot from anywhere in this to the second docking station. And then we consider the collision avoidance, having the both of them together. So 3 systems, fairly simple. Have a look at this one. The first one, in the first layer, we have got x, y, and phi, which is the x, y coordinate and the heading angle of the robot, giving a steering angle, theta 1, a steering angle, theta 2. Don't forget, one of the robots moves to the left, one of them moves to the right. And what we did in this system, we learned each one of them individually. So there was no second robot when we learned about the first system. Does this make sense? So the problem is broken into a couple of problems. First, control one robot to a docking station, then the second robot to another docking station, then both of them being on a space moving around, so not to collide with each other, and then finally slow down when you get to the docking station. So learn how to move one, learn how to move the other. I'm finished. Actually, I have got 2 transparencies. I'm very sorry to keep you at lunchtime. And then slow down at this here. So here it is, the first layer. We learned 125 rules for each robot to control from any position to the docking station. This is the first one, going to the first docking station. This knows how to go from anywhere to second docking station. These are the steering angles, the steering angle of the robot to get there. The speed is constant. That's why we didn't put the speed into the system. We didn't consider that. In the second case, the second set of rules that we learned, how to avoid. So the distance are given, in the distance between the 2 robots given to the system, and the system gives you the correction to the theta here. You see, theta 1 was the initial prediction of a steering angle without any other robot around. Now we make a correction. And the speed control. Because in many cases, what we notice is that even if you're coming with very slow speed, and this is a constant speed coming, sometimes the robot is in front of you. There's no time to turn around. You have to stop. You stop one, and the other one moves on. Right? So this is the steering angle correction and the speed correction. From constant speed, suddenly we give a correction. And finally, in the third layer, depending on the distance, this is the distance to the docking station. When you get close to the docking station, you slow down. You don't go in fast. Does this make sense? And actually it works because we're working with the robot soccer competition. So when the robot comes in towards the goal, you don't want the robot to go through the goal. You want it to stop, hit, and slow down. Okay? It doesn't work. We've watched many soccer competitions. Yes, as a human, when we shoot and we've got a goal, we run towards the goal. Very strange, huh? Some go to the goal, jump up and down. Robots cannot do. Robot hit, wait, stopped. In here, this is just going to the docking station. At the docking station, you control the speed. You slow down. Very simple. Anyhow, my message to you is it's possible to use fuzzy logic in many, many applications with large number of inputs. Imagine if you want to put all the inputs here, 6, 7, 8, 9 inputs, and this one had 5 fuzzy sets again. So you can calculate, large number of inputs. But in this way, 125, 125, 5, 5, 5. And actually it works very well. So finally, what we did was we applied the same thing, and there's lots of references in the paper that I believe is in the proceedings. I haven't seen it. We use it for traffic control, and actually we're working, the plan is that we will be working here with Dubai, a smart city on the traffic supervisory traffic control. And the traffic control, we look at controlling one traffic set using fuzzy logic, and then we look at 3 of them. So we just had the local controllers on each, and then they fit to each other. Multi-robot collusion avoidance, unemployment rate, housing price prediction, user profiling, very interesting. We use it in user profiling for web-based applications. Robot sucker that we really are stuck in it is very difficult because we get the inputs from the cameras, and things are really not working very well for us at the moment. Image enhancement and filtering, my friend Panus, we've done that. Maybe you want to look at our work in this area, maybe useful, I don't know. I'm not an image processing person, but actually one of the image processing professors gave us the problem and we looked into it. It was image enhancement. Cart balancing is the control problem, we've done that. And then closed loop control with 5 layers, that was done by my supervisor when I did my PhD. So I put in there, but I put in lots of. Anyhow, at the end, my message is that when you get a problem, try to break it into sub-problems, try to be gentle with the fuzzy logic, and then try to learn solve each sub-problems, and then combine them together. If you don't know how to combine them together, because there's an issue with the combinations, and depending how you combine them, you get different answers. And we have also published evolutionary algorithms and neural networks that you can use to basically tell you how to combine them together. But still, we don't have a solution that says, how do you have to combine them together? That's it. Can I make a suggestion? If you don't ask me any question, we can go for lunch. But you can ask questions. Is correct? Yeah.
I'm not a person who can. You can hear me?
Yes, you can use. The problem is that it's recorded.
Hello. Okay, thank you very much, sir.
I'll give you warning because within next day your picture and what you're saying will be on the web. All this.
Okay. I'm not, actually I'm working with the supply chain management. Inventory control and management is my broad area. And as per the fuzzy logics, I can say in computer science as well as in mathematics and everywhere, everyone is using fuzzy logics. But the thing is that we are using that. And the second thing is training data. Again, we are learning the process and training the data, then doing the prediction. Yes. Suppose the learning data, we have historical data and then we have a learning process. Yes. Then we will get something to predict. We are getting the patterns, this is the process, and then we will predict for the future. Yes. The thing is that if the learning of data is going wrong, we are getting the wrong graph, then again prediction is going wrong. We are basically, we are guiding the students. So, and my field is not fuzzy. But with the addition of the fuzzy, I will have good publications. Like if I will add in the title artificial intelligence and fuzzy logics, I will have good publications. But what is the contribution is there? The thing is that so many wrong things are going on, and then we are predicting wrong things accordingly. Yes. So kindly let me know, you have so many variables, so many parameters, thousands and hundreds you have discussed. But I am working hardly 4 or 5 parameters. That is my minimum requirement. Yes. But still I am struggling with the output and the patterns of the graph. Yes. And then parameters value and then optimization techniques. One addition to your topic extension of the application is the inventory control and management. We can do many things with the help of fuzzy logic. So can you tell me how we will guide the students so that they will understand the basic thing and the wrong learning graph, and then they are doing prediction wrongly, even though sometimes we don't have time to see all the things, and then we see that the whole work is done wrong, because after the results, when we will conclude, then we will see that results are coming reverse. Or sometimes in genetic algorithm you can say every time you run your logic or whatever your program, and if you have many parameters, it may take 1 day also if you don't have supercomputer or something. So you are getting the results after 1 day, and still you are getting nothing. And every time you are getting the new result because of the local solution. We are not getting the global solution always in the case of nonlinear problems. So this is my problem with the students, that please be crisp and have some simple examples, then have the results, then validate that, then only do some addition or something else. But as per the research papers and the books, nobody is telling anything. So many algorithms, so many things, and huge things. But I don't know, please help me.
Yeah, I will help you. My answer to you, sorry, Professor. My help to you is that what's presented in many conferences,
Yes, sir.
and what's, our friend Panos, presented on image processing, and there were like 10, 15 different methods that he compared his method against. I didn't, I'll just show you the solution. I haven't done it, just with the neural networks. There are many, many methods for solving different problems. Some are more suitable, so his algorithms at the moment gives better solutions for certain problems, and for some problems it's not good. So that's why we have so many statistical, we have got neural networks, we've got evolutionary learnings. All of them actually work. So you have to have a little bit of faith in what your students is doing, and look into seeing which method actually works better. Sometimes it's very difficult, I am a fuzzy logic person, so when somebody talks to me, I say, let's use fuzzy logic, and then for comparison, we do neural networks and we find out fuzzy logic was not good, Actually, if you think of publication, that's another publication, because I find that I failed. Yeah. It's not always that you're successful. But I can tell you something about fuzzy logic that really fascinated me with the robot control, is the inaccuracy in the data. So if you've got a little bit of sensor mistake or noise, and your input is not exact and correct, the fuzzy logic can handle it because of the way it converts the inputs into sets, and then based on how strong is your input, applies the output. So when we say the temperature is high, motor speed is high, depending on how high is your temperature, the motor speed is going to be high. Does this make sense? So this is not like I'm saying, if the temperature is 29, set the temperature, the fan speed to 2. You know what I mean? So if the temperature is 29, it could be 2, but when it is 28, or it is 30, what is going to be? Is it going to be 1 and 3? No, it's going to be just speeding your fan just a little bit more or a little bit less, not just changing suddenly. So that will give you a smooth answer. That's why it works. We all are great photographers now with very shaky hands. It doesn't matter. Next time you take a picture, shake your hand, and still you'll get a good picture. I can't. Remember, there has been days or evenings that I came home, I don't know how I find my way, but next morning when I look at the camera of images, it's perfect. Because it can handle noise. A little bit of movement, it adjusts your focus. Does this make sense? So you cannot do it with normal control systems. Neural networks can be used too. Which one is going to be better, we don't know. But what do you prefer? What do you prefer? Do you want to see the rules, or do you want to just have a system that just gives you the answer and it works? For many people, the industry says, give me something that works. I don't care, how it works. For me, I want to see the rules. But tell you the truth, with this system, with 5,000 rules, doesn't even make sense. There's 100, 150 rules you can follow, but 5,000 not follow. But it's not bad approach. So have a bit of faith in these solutions. They've been applied to many problems, and actually they work. So next time you're a student doing something that doesn't work, ask him to do something else and learn more.
Thank you.
We learn by failing also sometimes.
Thank you so much for a wonderful presentation, sir. And thank you for telling us about hierarchical and multi-layer fuzzy logic systems to develop them, like actually, right? Now I would like to request our chair and Professor Ajay Rana to step forward to felicitate our speaker. I would like to invite you, ma'am, also. Like, would you like to come? Because I think you
Yes,
belong to the
of
same
course.
area. Just come and just felicitate the professor.
Okay. I have, and the rest of you that are not in the picture, okay? I have always done it. I've done it in Noida. I've done it. Please come in the middle, please. May I just say something before the presentation? It works, Professor, because you are all my friends. I really feel great being among friends. I was in Noida, and actually,
stepping forward for the last group.
no, in 2 ways. One second. I have this condition. You know, because I want to measure the happiness of people listening to me. Okay, so I was in Noida, and I think it was 2,000 people listening to me.
I am waiting for the satellite, dear friend.
Yeah, I have got. Yes.
Still, I am
Yes,
not received.
That's right. I will send it. So, because if I ask you, you know, how was I? You all say great. You know, I can say, anybody that didn't like my presentation, raise your hand. I'm not going to ask you this, okay? And
But,
because
but,
many-
but I
but we
mentioned
take